Right, so in this lecture we're going to kick off our Python solution. So I've fired up a new Jupyter Notebook and I have included in here just a little bit of markdown in the very top cell just to give us a header, Truss example 1. Then I've imported the image in here just so we have a reference image so we know what we're dealing with. So if I double click that cell, you can see all that is a simple image import. So in the same directory as this notebook, I have a folder called img. And within that folder, I have an image file, an image PNG file called image1. And that's all I need to do to import that image. Okay, so the first real thing we want to do here is import some dependencies. So we're going to want to import various different libraries that help us out here. So I'm going to put in a little note here just to say dependencies. So the first one I want to import is not one I import very often, but I will now just for because we're going to need it to demonstrate something a little bit later on. I'm going to import copy. Now that allows me to make a copy of a variable. So if I, let's say, had a matrix, which I will have shortly, and I want to make a copy to that matrix, well, by importing the copy library, I can make a copy of it in memory so that when I edit the copy, I leave the original unchanged. So that's really all this is being imported for. Now, one thing I import into every notebook is the math library. So this gives us our basic math functionality. We then want to import NumPy, which makes it easy to work with arrays or matrices, which is going to be critical for this course, obviously. So we'll import NumPy, but we'll import it as an alias MP, so we only have to refer to MP. And then finally, we're going to import some plotting tools. So from the matplotlib library, we'll import pyplot, and again, we'll import that as an alias as plt, so we don't have to keep writing matplotlib.pyplot. Okay, so they're the only things that we want to import. We'll run that cell with Shift and Enter to make sure we haven't had any typos in there, so they've all imported fine. We also want to put in some constants. So in the same cell, I'm going to define some constants. First one's going to be Young's modulus. I'll define that as E, and typically, well, when we get to the end of this problem, I'm going to rerun this notebook with a value of E equal to 200 Newton or 200 kilonewtons per millimeter squared, which, because I'm working in newtons and meters squared, is going to be 200 by 10 to the 9. So that's 200 by 10 to the power of 9, and that's going to give me newtons per meter squared. Okay, and that's going to be a typical value for steel. Now, cross-sectional area, again, I'm going to just put in a number here. I'm going to say 0.005, and that's going to be meter squared. Now, they're the values I'm going to use at the end of this notebook, but to keep things consistent with the previous section where we kept Young's modulus and the cross-sectional area separate, I'm just going to put in values of 1 here. So our numbers are going to be consistent with what we saw in the slides in the last lecture. And then once we know we're happy with the code we've written for the whole notebook, we'll come back to the very top and we'll comment out these ones and we'll let the numbers be more realistic numbers. Now we can move on and actually calculate the elements, the global element stiffness matrices for element 1 first of all. So we can put a quick heading in first of all. So I'll do some markdown here. I'll change that to a markdown cell. And we'll go with element 1. Okay, and just for our own reference, this is from nodes 1 to 2. Okay, Shift Enter. And again, we're dealing with element, well, I should actually say element A because that's what I've referred to it as. So we'll go with element A, and that's from nodes 1 to 2. Now, the things that define an element are going to be the length of the element and the orientation, the angle. So I'm going to define an angle theta equal to, well, in this case, it's 0. And for a little reminder, that's going to be in radians. And then the length of the member, which we'll just define as a capital L, and that's equal to 3 because it's 3 meters long. So now we just have to build that stiffness matrix. Now you'll remember this is the element stiffness matrix measured in a global reference frame or defined rather in a global reference frame. So it was that matrix that was full of cosines and sines. Now for me to get a cosine or a sine, I've got to use the math library. So I'd have to do math.cos or math.sine. Now that gets very long and unwieldy. So I'm just going to define each one of those individual elements with its own variable. I'm also going to build this matrix up in different quadrants. So I'm going to start off, this will make more sense when you actually see that I've done it. I'm going to start off with the top left quadrant. So I'll just say top left quadrant. So you can refer back, but the top left quadrant had an element. Let's see, it was a square matrix. It was a 2 by 2, and so in that 2 by 2 matrix, which represented the top left quadrant, the first element, which we're going to call E11, so the element in column 1, row 1, was a cosine squared. So that would be math.cos of theta, and we squared that. Okay, so that was the first element. Now in that top left quadrant, the element that was in row 1, column 2 was a cosine theta times a sine theta. So I'll define that next. The element in row 2, column 1 of that top left-hand quadrant was the same. So I'll just say 2, 1. That was the same. And then the element in row 2, column 2 of the top left-hand quadrant was sine squared. So I'm a fan of, probably not best practice, but I'm a fan of just copying and pasting whenever I can. So that's going to be E22, and that was going to be sine squared. Okay, so that's the top left quadrant. So we can now combine those elements into a matrix. So what I'm going to do now is I'm going to say K11, so that refers to the top left quadrant for elements that goes between nodes 1 and 2. And that's going to equal to E times A over L times the matrix itself. Now I'm going to define that matrix using a NumPy array. So from the NumPy library, we're going to have np.array, and we're going to define an array, a two-dimensional array. So we first of all put a set of square brackets to define an array, and then we define the top row of that array with a further set of square brackets, and then a comma, and then a second set of square brackets gives me the bottom row of that array. So we'll just fill in our elements here. We've got element 1, 1, element 1, 2. So that's elements in row 1, row 1, column 2, and then the same idea for the second row of our matrix. Okay, and that's the top left-hand quadrant of the stiffness matrix defined. It's pretty straightforward. So we just repeat this process for the top right quadrant, bottom left quadrant, and bottom right quadrants. The exact same process again. So I'll speed through that and save you the pain of watching me type it all out. Okay, so that then defines that stiffness matrix, that global stiffness matrix for our element. Now all we have to do is take these 4 different quadrants and concatenate them into the overall global stiffness matrix for that element. So we're going to do this in 2 steps. We're going to first of all combine K11 and K12 together. So we're going to combine those two into one matrix. So that's essentially concatenating the top 2 quadrants together to form row 1 and row 2 of our global stiffness matrix. We're going to do the same for the bottom 2 rows by concatenating K21 and K22. And again, if you're not familiar with the term, concatenate just means to join together 2 elements, in this case 2 matrices. So once we've got the top 2 rows concatenated together and we've got the bottom 2 rows concatenated together, we're going to concatenate the 2 of those together to obtain the complete stiffness matrix. So again, you'll see what I mean here as I start typing this out. So let's start off by concatenating K11 and K12 along the vertical axis. So along the vertical axis simply means to join them side by side. Right, so we're going to define these 2 rows as top, because these are the top 2 rows, and we're going to take from the NumPy library the concatenate function, and we're going to feed into that function K11 and K12. So in a set of brackets, K11 for member 1, 2, and K12 for member 1, 2. So we're going to concatenate those together, and we need to tell this function that we want to do it along the vertical axis. So these are concatenated side by side, and for that we simply put in axis equal to 1, where axis 1 would be the column axis. So if I run that, okay, it all works okay. Let's just print out what we get. Well, actually, we'll print K11 first of all. So what does that give us? Okay, that gives us our square matrix we fully expect. Let's print out below that K12. And again, another square matrix, that's fine. Now let's print out, just to visualize what we get when we concatenate those two together. So we'll print top. So we should get a matrix with 2 rows and 4 columns. And indeed, that's what we get. So we've got our first row here and our second row here. So those are the first 2 rows of that element stiffness matrix. So it was a pretty straightforward operation. We're going to do the exact same thing to concatenate the bottom 2 rows. So we'll start off by copying this thing and editing what we need. Okay, and then what we're going to do, we'll call it bottom. In fact, let's shorten that to BOT. And now we want to concatenate those two together. So let's say concatenate top and bottom along horizontal axis. And I'll just say BTM here. Okay, and we're going to define this thing as K1G. So it's the global stiffness matrix for element 1. And again, from the NumPy library, we're going to take concatenate. We're going to feed it in top, bottom, and we're going to tell it we want to concatenate along the horizontal axis, misspelled axis, and that's going to be axis equal to 0. Excellent. So now let's just print that thing out. So I'll print ourselves a little statement here. So the global stiffness matrix for element 1. And then we're going to print out the stiffness matrix itself. So let me see, let's print out K1G first of all. What do we get? Okay, excellent. That's the matrix we want. Now we want to just tidy that up a little bit. So I want to round out these numbers. I don't want all those decimal places. So I'm going to round it to 3 decimal places. So what I'm going to end up doing is I'm going to, from the NumPy library, right? From the NumPy library, I'm going to take the function round, and that function takes the argument, it takes a couple of arguments. The first argument is the thing that I want to round, and then the second argument is the number of decimal places I want to round it to. So if I print that now, we get something a little bit neater and tidier to look at. Now, it's important to know or to recognize what I've done there. I've not rounded the actual value itself, right? I've not rounded the source variable K1G. So in subsequent calculations, when I refer to K1G, I'm going to get all of the decimal places. I've only rounded out the thing that I'm actually printing to screen. So it's important you don't lose any information by rounding out the source element. You just round out what you're printing to the screen. Okay, so that's the global stiffness matrix for element 1. Fairly straightforward. Now the beauty of programming is going to come into play, because in order to do this for element 2, I'm simply going to copy and paste all of this code, and I'm going to just change the length, and I'm going to change the angle, and I'm going to let this Jupyter Notebook do the hard work for me. So I'll put in a quick heading just to say that this is element B, which goes from nodes 2 to 3. I'll change that to a markdown cell. Shift enter. Okay. So as I said, I am literally going to copy all of this straight into here. All I'm going to do is change the angle. So the angle is 2.2143 radians, and the length of this member was 5 meters. Now I just got to skim through this just to make sure that I've got all the correct labels. So this is going to be for member B, which goes from 2 to 3, same here, 2 to 3, and so on. Okay, that means I need to change these down here also. Right, what else do I need to change? That needs to be K2, and we'll print out K2, and let me see, I change that to 2. Okay, let's run this thing. And that's exactly what I expect. So you can refer back to our slides in the last lecture, and you'll see that was the stiffness matrix we got for element 2. So that's all we want to cover in this lecture. We've built the 2 element stiffness matrices. Now we're going to end up coming back and refactoring all of this code to make it much more general. So we won't actually have to write a code cell for every single element in a structure. As you can imagine, that would get very, very long and tedious in itself. We'll come back to that a little bit later. But for now, that's all we wanted to do. We wanted to take our first steps into Python and solving this thing through code rather than sort of longhand writing it out. Okay, so we'll leave that there for now, and we'll pick it up again in the next lecture.